I'm Antonio Sala, and in this video we'll discuss a first demonstration of a linear matrix inequality code in Matlab, computing the smallest ellipse that contains a set of ellipses and polyhedrons. In this first video, we'll just discuss the concept of smallest, meaning the ellipse with minimum largest semi-axis. So we will wish to fit the ellipse into the smallest possible circle. Then in a second video, we'll refine the idea and we'll also speak about the minimum volume, in this case minimum area ellipse, containing these other polyhedra and ellipses. The software we are going to use is Matlab plus Yalmip and Sedumi, with the versions you see on screen. I installed them using TBX Manager, but okay, it's up to you to consult the web for installation, Matlab path, etc. issues in order to be able to run the code in this example, which you are able to download if so wished from the link in the video description. So let's go. Just a note, for simplicity, we are only going to consider polyhedra and ellipses centered at the origin. Also, the problem can be generalized to deal with ellipsoids and polyhedra not centered in the origin, but as my overall goal is introducing linear matrix inequalities for control purposes, in most control problems we just set 0 as the operating point, and disturbances, uncertainties or whatever are symmetric around the origin. So the LMIs for symmetric stuff will cover 99% of the cases I'm thinking for in later applications. But of course, you can search bibliography for the non-centered version. Good. So, we'll start with the polyhedron. The polyhedron is the convex hull of some vertex points, and we may also have some other points. And the convex hull is the smallest polyhedron containing all the points. So even if I have 5 points, these 5 points will define a 2D polygon with 4 vertices. Also, a polyhedron may have a so-called face representation as an intersection of half planes. Say, I will have the intersection of this half plane, this half plane, this, so this 4-side polygon in 2D can be described as the intersection of 4 half planes, and that would be the face representation. But in this case, we will not use the face representation of a polyhedron, we'll use the vertex representation as follows. I will define these vertices, and well, as I am discussing everything symmetric around the origin, I will add the negated ones, so I will have 10 vertices. In these 10 vertices, 2 of them will be actually interior points of the polyhedron they define, because if I compute the convex hull with this Matlab command, the results are a polyhedron with 8 faces from point 2 to 4, 4 to 5, 5, 3, 3, 7, 7, 9, 9, 10, 10, 8, and 8, 2. You can see that this 2 is repeated here. So we have 8 faces, 8 sides in a 2D polygon, and 8 vertices. And as you can see, points 1 and 6 are interior because they are not in the convex hull. So my vertices here define an irregular octagon with a patch command using only the vertex that the output of the convex rule command tells me that they are on the edge, it will plot this cyan polygon, and I will define a positive definite matrix M, just invented. So the constraint x transposed mx lower than or equal to 1 will define an ellipse whose boundary will be the equality plotted with f implicit as this dashed red ellipse below the polygon. So my problem statement will be obtaining the smallest ellipse, in some sense, let's say, this yellow ellipse, which contains the cyan polygon and the red ellipse. Data for the cyan and red ellipse are assumed to be known, and the matrix defining the yellow ellipse will be my unknowns, and I will obtain them via linear matrix inequality calculations. How? Well, our target ellipsoid thing, well, ellipse, we are in 2D, but this can generalize to higher dimensions. We'll have an ellipsoid with a symmetric matrix P, and we will define that as decision variable in Yalmip with the sdpva command. It's an unknown matrix that it is by default symmetric, so it encodes 3 scalar decision variables that my solver must find. Our first constraint will be that P must be a positive definite matrix, so I get an ellipse. So I am saying that the minimum eigenvalue of P must be greater than, let's say, 10 to the minus 6. Actually, this condition is redundant. More on that later. But it's important to conceptually understand that P must be a positive definite matrix to define a non-degenerate ellipse, and that even if in this problem we later see that it is not actually needed, in other kinds of geometric or control problems this constraint may be explicitly needed. So we highlight it to avoid forgetting this important fact. So once we have defined our main unknown, in order for this ellipse to contain the vertices, of course, each of the 10 vertices will need to fulfill the ellipsoid equation. This is why we will use the vertex description of the polyhedron and not the face description. So I have 10 vertices, and I will add these 10 constraints, which are the Matlab way of inserting that constraints, and this is a linear matrix inequality constraint on P, because P appears linearly. In fact, this constraint is actually just an ordinary linear constraint. For instance, if we had, let's say, V1, 3, 4, V1 transposed P, V1 will be, recall that P is this thing here, well, this will amount to be 9 P11 plus 24 P12 plus 16 P22 lower than or equal to 1. So this is actually a linear constraint that you would encounter, let's say, in a linear programming problem. In fact, linear matrix inequalities have linear programming as a particular case. Well, the thing is that we get 10 constraints like this, one for each vertex. Actually, we would need just 8 of them, the 8 outer vertices, because as both the polyhedron and the ellipse we are seeking are convex bodies, then if the ellipse contains the outer vertices, then it of course contains all the interior of the polyhedron. But okay, for simplicity in the code, I didn't use any convex hull modification in here, because in fact, as linear matrix inequalities are very computationally efficient, convex programming, maybe just putting all vertices and doing LMIs might render faster than computing convex hull stuff. Code efficiency is not the topic of this video, neither it is my specialty, but LMIs may be way more efficient than some polyhedron manipulation stuff. So with this thing, we have encoded that the polyhedron must be inside the short ellipse. Next, if we want this ellipse to be inside this ellipse, then from ellipse theory, in fact we have another videos in this collection devoted to it, the thing is that intuitively, if p is multiplied by 4, let's say, then x is divided by 2 in order to keep this inequality. So the larger p is, the smaller the geometric body it represents renders. So the small ellipse will need to have the larger matrix, so matrix M must be larger than matrix P, formally interpreted like this: M minus P must be a positive definite matrix, and this condition is necessary and sufficient for ellipse P being larger than ellipse M. So we append that last LMI condition to the set of constraints. This is actually a matrix constraint, a matrix that must be positive semi-definite. These kind of constraints are the ones that you cannot add into linear programming, simplex stuff. This was an inequality between scalars. You can handle that with linear programming code, but this inequality regarding eigenvalues of a matrix, you cannot handle it with linear programming stuff. You need semi-definite programming, linear matrix inequality toolboxes. But okay, it's linear matrix inequality because P appears linearly. We don't have P squared, P inverse, or that kind of stuff. So good, we have all LMI constraints, and now defining the problem statement that my ellipse must enclose the polyhedron and the ellipse, we must encode the fact that we wish the smallest possible ellipse. In this first video, we'll understand as smallest the ellipse that fits in the smallest sphere, so the largest semi-axis of the ellipse must be made as small as possible. That's equivalent to including the ellipse in the sphere of radius rho and making rho as small as possible. Then, with the same argumentation we had here, sphere of radius rho has this multiple of identity matrix defining them, so you can pause and think or look at the relevant materials in this collection or in other literature to realize that this constraint makes my ellipse to lie inside a circle of radius rho. So we must minimize rho, but okay, instead of minimizing rho, subject to this non-linear constraint in rho, we cannot do that without further manipulations with LMI software, but okay, just changing the name and denoting as beta, the inverse square radius, then minimizing rho is equivalent to maximizing beta, so we'll maximize beta. subject to this linear constraint in both p and beta, and then that can be easily handled with linear matrix inequality software, because this is an LMI constraint, and my objective function, minimizing beta, is linear in my decision variable beta, so no problem for Yalmip and Sedumi, and this is the way to do it. I'm adding this constraint, appending it to the list of prior linear matrix inequality constraints I had. Of course, I need to define a new decision variable SDP var beta scalar, and then this is the cost index that Optimize tries to minimize. So maximizing beta is the same as minimizing minus beta. So with this we maximize beta, subject to the polyhedron ellipse inclusion in my problem statement, plus this shrinking sphere containing everything. And then my solver, in less than 50 milliseconds, provides a successfully solved solution with this value of p as the ellipse we wished to obtain. If I represent the solution, this is the ellipse I have obtained, yellow down there, and this is the multiple of identity defining the smallest circle I was shrinking, and of course my final ellipse is basically that circle. This is the smallest circle including everything. You will say, okay, can you somehow shrink the ellipse a little bit more? Because, you know, if you minimize the maximum half axis, then the minimum length half axis is kind of free. Indeed, this is a convex optimization problem, but the solution is not unique. So, kind of formally correct, but intuitively this is not the smallest ellipse. So, trying to shrink in the shorter axis or to minimize the area of the ellipse will be, for brevity here, the objective of a sequel video on this problem. And here we'll finish. We have just discussed how to set the problem of the smallest ellipse, smallest as smallest maximum half axis, containing the cyan and red stuff. We have discussed how to encode it as linear matrix inequality with this positive definiteness condition on P, with these scalar inequalities, one for each vertex point we wish to be inside the ellipse, and with this matrix inequality regarding ellipsoid inclusion, and we added this condition to be inside the given sphere, and we shrinked that sphere, well, that circle, putting that cost index into the optimize command, and in a few milliseconds we got a solution we will refine in the sequel video. For the moment being, we end here. Thanks for watching.